One of the greatest maritime disasters in U.S. history was the engineering catastrophe of the Sultana, a deadly combination of several oversights and unfortunate occurrences. This steamboat, launched on January 3, 1863, was the fifth steamboat to bear the name. Its design optimized speed and capacity as the vessel was 260 feet long, 39 feet wide at the base, and 42 feet wide at its longest cross-section. Having the capability of displacing 1,719 tons of water, a 7-foot draft, and a crew of 85, the Sultana was powered by two side-mounted paddle wheels, which were driven by 4 fire tube boilers, a new design capable of producing more power with less fuel. The Sultana usually transported passengers and small amounts of cargo, such as sugar and livestock. Its legal passenger capacity was 376 individuals. During its time near the end of the Civil War, the steamboat would transport Union prisoners of war from the southern United States northbound. This marks the beginning of failure. On April 21, 1865, Sultana embarked from Vicksburg, Mississippi, to New Orleans, desiring the profitable venture of returning paroled prisoners. However, 10 hours into the journey, one of the 4 fire tube boilers sprung a leak, depressurizing the vessel's engine and leaving the ship to barely make it to their destination. After docking in Vicksburg, the head engineer of the ship reached out to a mechanic for boiler repair. Due to the severity of the repair, it would likely take a few days to cut and properly fix the ruptured steam. The monopoly on returning the prisoners, however, could not wait a few days. A temporary repair was deemed suitable for the time being. In this case, the bulged boiler plate would be hammered back into place with a 1/4-inch patch riveted over the busted seam. This was completed within 1 day and coincided with loading the passengers and cargo. The original calculation for the number of prisoners the ship could hold was estimated to be 1,400. On that day, the ship held 1,960 prisoners, 22 guards, 70 passengers, and its 85 crew, totaling 2,137 individuals packed into every available space, as well as the 120 tons of sugar in the hold. The sheer weight caused the decks to creak and sag beneath them, requiring large wooden beams to support the floors. In addition to the state of overload, the ship traveled 2 days against the flow of the Mississippi River, which was in one of the worst flood stages ever seen, as the spring weather was melting the upriver ice and snow. Riverbank trees were almost completely submerged, as only the tops were visible. To make matters worse, the Sultana's hold and decks were emptied of its 120 tons of sugar and 200 men early into the trip, leaving the vessel not only overloaded and in a difficult environment, but also top-heavy. The ship was now listing heavily within the river.
At 2 a.m., April 27, 1865, north of Memphis, a boiler exploded with 2 more following it almost immediately. The incredible amount of energy behind the pressurized steam and the flash-boiling water demolished the pilot house, leaving the Sultana burning and unpiloted. Soon after, the twin smokestacks fell opposite to one another, one into the new hull and the other into the crowded upper deck. The broken wood and varnished surfaces quickly caught aflame, turning the once proud ship into a conflagration of fatigued and panicked souls climbing over one another into the icy torrent beneath them. After several hours and a few rescue attempts, the boat sank near Mound City, Arkansas. Although the exact number is unknown, this tragedy claimed upwards of 1,200 lives. A severe combination of factors led to the failure of the Sultana. The first can be traced back to the faulty repair of the boiler. The material of the boiler was charcoal hammered No. 1 iron, a metal that was exposed to prolonged heating and cooling, which will harden and become brittle. Being that the ship was listing severely and the boilers had to be run hotter to drive the enormous weight, The water levels within the connected boilers had to be carefully monitored so that hot spots would not form. The steamboat swing forced water from the highest boiler to the lowest boiler, with each of the fires still burning at the same intensity. This created hot spots within the metal that would then flash boil the water into pressurized steam when the ship rectified itself. This constantly superheated and cooled the material into brittleness, likely causing the temporarily repaired boiler to be unable to withstand the pressure, explosively failing into destruction. The second factor to take into account is the use of sediment-ridden river water to be turned into steam. The sediment within the water would clog between the flues rather easily, increasing the pressure artificially. This sediment would also sink to the bottom of the boiler, creating hot spots which would embrittle the material. The third factor is the diameter and proximity of the boilers to one another. Each boiler was constructed with 24 5-inch flues so closely packed to each other that cleaning was incredibly difficult and inefficient, especially due to the sediment buildup. The inability to clean the flues led back to factor 2, creating hot spots, which ultimately failed the material. Soon after the Sultana incident, 2 other steamboats exploded with tubular boilers and the same design. This design was discontinued for steamboats, as well as charcoal hammered No. 1 steel 4 boilers.
A number of things could have been done differently to avoid disaster, but from a materials and engineering perspective, there are still a few possible solutions. Material selection is vital for this application, as you would need something to withstand the constant high temperatures and stress from the heating element, superheated water, and high-pressure steam. This means the material needs a relatively high yield strength, an alloy steel with a hardness to resist impact, good processability for ease of production, high toughness against brittle failure, and a small to medium uniform grain structure to encompass all these properties. A possible material for this application would be chromium molybdenum alloy steel. Obviously, this material would not have been available in the 1860s America. However, as a modern application, this is an incredibly effective choice. The molybdenum adds strength to the material as well as the ability to withstand high temperatures. Chromium helps oxidize the material and keep it from corroding. Both of these elements together promote a greater hardness in addition to being the choice for steam temperatures greater than 500 degrees Celsius in power stations. With all these properties together, the material could easily withstand the stresses and strains without significant plastic deformation. The stress strain curve above shows the relative ratio of stress to percent elongation of chromium molybdenum alloy steel as temperature increases. The boilers on the Sultana usually reached around 400 degrees Fahrenheit, or 204 degrees Celsius, which still rates around 1,000 megapascals in yield strength. The point at which the yield strength occurs also occurs around a decent strain of 6 to 7%, allowing the material to have a bit of space to expand without plastically deforming. The brittleness caused by cyclic heating is difficult to mitigate. However, a design change may be the best solution, as it would mostly avoid the issue. Being that steamboats gyrate by nature, having a stable water level would be challenging in a horizontal system, such as the Sultana. A vertical system with less clustered flues would be easier to maintain and keep the water level more consistent. By controlling these issues, hotspots would be significantly reduced, if not mitigated altogether.
In conclusion, the design of the Sultana could be drastically improved. A few ways include different shapes for the boilers, a stronger material that can withstand the temperature swings, as well as clean water lacking sediment that could block the flues. The Sultana has allowed us to learn a lot about materials, and hopefully we can keep similar tragedies from occurring.